Hey, hey, hey! In this video, we are going to continue into our identities unit, dealing with a lesson that comes from Chapter 9, Section 2 in your book titled Addition and Subtraction Identities. Now, we have worked with a whole host of trigonometric identities. Those are the equations that are always true, no matter what value you use for the variable, all the way from the reciprocal identities to the quotient identities, the Pythagorean identities, and beyond. Today we will learn two new families of identities, the addition and subtraction identities. And the reason they're called that is because they deal with the sine, cosine, or tangent of a sum of two values. Maybe the sine of an x plus a y, or maybe the cosine of an x minus a y, just to throw some variables in there. Addition and subtraction of two values that are within your sine or cosine function. Now, those identities can be easily mistaken by assuming that this equation here is true. Is the sine of x plus pi equal to the sine of x plus the sine of pi? Is this side always equal to that side? Well, we can check that by graphing. And we did that a little bit in a previous video. An identity can be tested graphically if you graph each side simultaneously as two separate graphs. So as y1, I have the sine of x plus pi, and as y2, I have the sine of x plus the sine of pi. When I hit graph, if these two curves, there's the word I was searching for, are identical, then this equation is a true identity. So here comes the first graph, y1, and here comes the second graph, y2. Those two curves did not match, which means the expression on the left and the expression on the right is not a true equation. Now, identities should be true no matter what you plug in. So here's the conclusion I can make from that little graphing exploration. The first conclusion is that I can't turn two pieces of paper. Here we go. I can conclude that since the sine of x plus pi was not equal to the sine of x plus the sine of pi, that the sine of x plus anything else will not be equal to the sine of x plus the sine of y. Identities should be true no matter what you plug in for the variable, and we just saw that if I plug in a pi here, that the left and the right-hand side do not match. Therefore, this is not a true identity. There are, however, identities that deal with the sine of x plus y, or maybe the cosine of x plus y, and those identities can be found in your book on page 584. And I'm going to run through them here, but you might just want to pause the video so that you could add these to your notes. The sine of x plus y is actually equal to the sine of x times the cosine of y plus the cosine of x times the sine of y. There is multiplication happening between these individual sines and cosines. The dot is just not included. The subtraction identity for sine, that would be the sine of x minus y, is equal to the sine of x times the cosine of y minus the cosine of x times the sine of y. And it might be helpful to think of these x's and y's as angles. Sine of this angle plus that angle is equal to sine of x angle times the cosine of y angle, and then the cosine of x angle times the sine of y angle. Cosine has its own addition and subtraction identities. And these four identities are ones that you do not need to worry about trying to memorize. You will be allowed to use these from your notes or maybe from a separate sheet when we get to trying to take some sort of an assessment on this information. You should familiarize yourself with working with these, but not memorizing them. Now, when it comes to working with these identities, what will we have to do with them? Well, there are three things that we're going to use these addition and subtraction identities to do in our trigonometric work. The first of which is to determine the exact value of the sine or cosine of an angle that is the sum or difference of a special angle. These identities can be used to help us determine the exact values for the sines, cosines of a particular angle if that angle is the sum or difference of a special angle. We can also use these addition and subtraction identities to rewrite and simplify expressions, as we've done so with some of our other identities. And we can also use the addition and subtraction identities to prove other equations as true identities. In terms of the three sort of learning targets that this particular lesson entails, today's video will only cover this first one, using the addition and subtraction identities to determine the exact value for the sine and cosine of an angle that's the sum or difference of a special angle. Little side note here, notice that I'm only talking about the sine and cosine. There are addition and subtraction identities for the tangent. However, we will not be covering those in this identities unit in trigonometry. Now here's the first real example when it comes to using our addition and subtraction identities. We are asked here to find the sine of 13 pi over 12. And they've asked us to use the addition identity to find the exact value. So I cannot just take my calculator, type in sine 13 pi over 12, press enter, because that would not give me an exact value. That would give me a rounded approximate value, and that's not what they're asking for right here. 13 pi over 12 is not an angle that I've worked with before. When I think back to my unit circle, and all of the angles that we navigated around on that unit circle, 13 pi over 12 was not one of them. So here's how we can use the addition identity to evaluate the sine of 13 pi over 12. In order to use an addition or subtraction identity to find exact values, first write the angle as the sum or difference of two angles for which exact values are known, such as pi over 6, pi over 4, pi over 3, pi over 2, pi, and any multiples of that. So in order to evaluate exactly the sine of 13 pi over 12, here's what I must do first. I must take that angle, 13 pi over 12, and I should rewrite it as either the sum or the difference of two angles for which exact values are known. So I'm going to take 13 pi over 12 and rewrite it in terms of two angles that I know the exact sines and cosines of. Since 13 over 12 is bigger than 1, I'm going to use addition to rewrite this, plus they hinted to me use the addition identity. So I'm going to think about what values I can add together that would make 13 pi over 12, and I want to make sure that those values are angles that I can find the sine or cosine of exactly. And one way to do that would be this. I could use 4 pi over 12 plus 9 pi over 12, because those two angles add up to make 13 pi over 12, and when I simplify those, they reduce to pi over 3 and 3 pi over 4, two angles for which exact values are known. And you may need to go back and review some of the exact values for the sine, cosine, and maybe even tangent, but not as much for these two angles. Next, I am going to use my addition identity and substitute pi over 3 in place of x and 3 pi over 4 in place of y in that identity. So I have found two angles that I can rewrite this one as, and those two angles have exact values for sines and cosines that I know. I'm going to write those two angles down on my work page here so that I don't forget what they are. X will be replaced with pi over 3, and y will be replaced with 3 pi over 4. Now I can just bring this back up, and I'm going to write down that addition identity so that I know what it looks like when I go to replace each x and y. So I know that the sine of x plus y is equal to the sine of x times the cosine of y plus the cosine of x times the sine of y. Some classic pen juggling there. Now I have found that 13 pi over 12 can be expressed as pi over 3 plus 3 pi over 4. And let's replace each x and y with those values. This becomes the sine of pi over 3 times the cosine of 3 pi over 4 plus the cosine of pi over 3 times the sine of 3 pi over 4. And then to simplify, I evaluate these sines and cosines exactly because they represent angles that I know the sine and cosine of in an exact manner. So I've taken this identity and used it to rewrite the expression I'm trying to find the value of. Continuing, I know the sine of pi over 3 is root 3 over 2 times. I know the cosine of 3 pi over 4 in the second quadrant is negative root 2 over 2. I know that the cosine of pi over 3 is 1/2, and that the sine of 3 pi over 4 in the second quadrant is where we find the angle, 3 pi over 4, is positive root 2 over 2. Next, I'm going to continue my simplification by performing this multiplication here. Root 3 times negative root 2, a reminder from some of your previous algebra that radicals can be multiplied, that denominators in your multiplication here should also be multiplied, plus 1 times root 2 is root 2, 2 times 2 is 4. Since my fraction does have a common denominator, I can unite this as one single fraction. My numerator, however, is not two like terms, so I can't add these numbers together. You can only add or subtract like radicals, just as you can only add or subtract like variables. So I end up with negative root 6 plus root 2 all over 4. And that number there represents the exact value for the sine of 13 pi over 12. That number there is not as clean looking as root 3 over 2, but it is an exact value. And I could verify that for you on my calculator. I'm just going to set it down, I think. If I evaluate in radian mode the sine of 13 pi over 12, it is approximately negative 0.2588. And I also take negative root 6 plus root 2 and divide that by 4, I get the same approximate value. So I have evaluated the sine of an angle that I normally would not be able to work with by rewriting it as a sum of two angles that I do know. Next, let's do another example of that same sort of work, but I'm going to go a little more efficiently through that one. And again, the hardest part sometimes turning the pages. So now find the cosine of negative 5 pi over 12. My first task is to rewrite negative 5 pi over 12 as the sum or difference of two angles that I know the sines and cosines of. Since negative 5/12 is a negative number, I'm going to use subtraction to do that. So I want to think about two numbers that subtract to make this, but those two numbers have to be angles that are going to simplify to values that I can work with exactly. And sometimes this is the hardest part, to be honest with you. Finding the angles that represent this one, but also can be worked with exactly. And you might have some trial and error. You might try something that doesn't work. For me, I'm going to think 3 pi over 12, which reduces to pi over 4, minus 8 pi over 12, which reduces to 2 pi over 3. So that feels pretty good. So I've got pi over 4 minus 2 pi over 3. And I'm going to forego as many pretty colors as I did last time. X will be replaced with pi over 4. And do take note here that y will be replaced with 2 pi over 3, not negative 2 pi over 3, positive 2 pi over 3. I'm not subtracting a negative number, so I don't use a negative number here. I use 2 pi over 3. I will write out the cosine subtraction identity, but I'm not going to go pretty colors like I did last time. The cosine of x minus y is the cosine of x times the cosine of y plus the sine of x times the sine of y. All x's replaced with pi over 4 and all y's with 2 pi over 3. Here we go. This becomes the cosine of pi over 4 times the cosine of 2 pi over 3 plus the sine of pi over 4 times the sine of 2 pi over 3. Next, I evaluate these sines and cosines exactly because they all represent angles that I can work with exactly. And you may need to go back and review that, look at your unit circle, review those coordinates where these angles pass through. Remember that the x coordinate is the cosine of that angle and the y coordinate the sine. The cosine of pi over 4 is root 2 over 2. The cosine of 2 pi over 3 is negative 1/2. The sine of pi over 4 is root 2 over 2. And the sine of 2 pi over 3 is positive root 3 over 2. We will simplify this as we did the previous one, multiplying our numerators and our denominators, multiplying our numerators and our denominators, and then using that common denominator to write this as one single fraction, but knowing that I can only add together like terms. That means that the cosine of negative 5 pi over 12 is equal to negative root 2 plus root 6 all over 4. I'm going to sneak in one final example in this video because it's going to kind of tie into things that we're working with in the future, and that's this one here. Rewrite the expression in terms of sine x or cosine x. Currently it's written as the cosine of x minus pi over 2. I'm going to rewrite it using the subtraction identity. X will stay x because they want an x in the expression, but this pi over 2, I'm going to use that as the y in my subtraction identity. Now I just wrote that subtraction identity down in the last example, so I'm not going to rewrite it, but I will show this replacement here. It would become then the cosine of x times the cosine of pi over 2. Remember, positive, not negative, because I am not subtracting a negative, plus the sine of x times the sine of pi over 2. So it's almost as if, well, you've got one angle that you can replace, but the other one you can't. And that's okay, because our final answer will be in terms of x. Now I'm going to evaluate the two expressions here that I can. This would become the cosine of x times 0, because pi over 2 has a cosine of 0, plus the sine of x times positive 1, because the sine of pi over 2 is 1. Anything multiplied by 0 is 0, and anything multiplied by 1 stays the same, showing that this expression can be rewritten as the sine of x. All of your work today will mimic those examples that we've seen here. and they will all use these identities, the sine addition and subtraction, or the cosine addition or subtraction. Have a great day.